Okay, well, great. So we're really going to change bases and go from the lofty and conceptual to the very practical. And that was the way that I looked at this. So I was asked to discuss issues associated with the scalability of CCS in the context of application with biomass. So that's what I will do. And also, always the backdrop that I bring to these kind of discussions is what are the implications for fundamental R&D that would overcome some of the big hurdles that we identify as we study these issues. So to get started, what I'd like to do is to talk about some of the key issues facing the large-scale deployment of BECCS. And so I want to start this by comparing sort of the mental framework for CCS with fossil fuels, and then what I imagine as one implementation of CCS with biomass feedstock. So here's a table that sort of shows the comparison. So if I think about CCS with fuels, and I'm including co-firing. I thought Larry had a wonderful discussion about the real benefits of co-firing as a strategy, because it's much simpler, I believe, than the alternative. But okay, so what do we think about? We think about large central power generating stations or large industry. So we're thinking in the 100 to 1,000 megawatt scale of plant, which means we're sequestering something on the order of 1 to 10 million tons of CO2 per year. So that's on the generating side. And then if we think about the fuels, basically the plants are operating fairly efficiently, maybe in the 35 to 40% efficiency range, or if it's combined cycle gas, it could be 60% efficient. We have reliable fuel delivery systems that we've spent decades creating efficient supply chains. So and the fuels are not very variable. Yeah. And then we operate these basically year-round, with the exception of maintenance periods. So that's sort of the conceptual model for CCS with the fossil fuels that many of us have been spending about a decade or more working on. Okay, compare that to at least one possible implementation of BECCS. So with biomass feedstock. So it's potentially on a smaller scale. We heard earlier today that sort of 50 megawatts, or sort of 1/10 the scale of a typical fossil fuel power plant. So what that means is the amount of carbon dioxide is sort of something on the order of less than 1 million tons of CO2 per year. Second thing is there are going to be lots of logistical issues associated with the scale-up of the biomass feedstocks, which might make it so that they vary over the time of the year. It might also mean, well, probably would mean, that we'll have variable fuel sources. So it's a different biomass, and so how do we deal with that? And again, the operations over the course of the year may be variable depending upon the total availability of biomass. So that's not to say that biomass couldn't be operated in a very different way, much more like a fossil fuel plant. But one implementation is this smaller scale implementation. So so I sort of looked at it and I said, well, could we do this if we were really thinking of downscaling CCS? What are some of the issues you'd have to deal with, and how might that impact cost? And then how would that influence sort of projections now about how much BECCS we may actually do? Okay, so just again, some very practical things to start off with. So before you would commit to building a plant, you would need some kind of commitment of biomass feedstock on the order of, say, 30 years. And obviously, you'd want to run longer. So when you go to the bank to get the financing for your project, so that's an issue we have to deal with. The other thing is what about the flue gas composition? It's not going to be the same as the flue gas composition for fossil fuels. And also, the flue gas composition may vary depending upon the biomass feedstock. So that creates some other challenges. The other thing is, if we're imagining this implementation of these smaller scale BECCS projects, the co-location of the geologic storage resources with the demand for electricity or heat and biomass resources has to be pretty good. And earlier today, that was referred to as the match. We have to have a good match between all of these things. And then finally, we have to be able to cost-effectively scale up, or actually in this case, scale down, each element in the BECCS technology chain. Okay, so that's the backdrop, the way I've been thinking about the issue. So briefly, which we all know, CCS involves 4 steps: the capture, compression, pipeline transport, and geological sequestration. I will say briefly a little bit about some other storage options that may be considered. And what I'll do is I'll just go through these one at a time and look at how that might be different if we're implementing it in the context of BECCS. Okay, so capture, probably 75% of you know what the options are, but for those of you who come from a different background, there are 3 primary technologies, and actually we heard about a very elegant 4th technology today, the cryogenic separation. But there are basically 3 different ones that have been invested in heavily thus far. One is post-combustion, so you basically just burn your fuel like you'd burn it today, and you put in some kind of scrubbing unit on the downstream end. Another option is pre-combustion capture, or basically gasification is how it was referred to earlier. And then the 4th option, or the 3rd option, is oxyfuel-combustion, where you first separate nitrogen from, or actually oxygen from air, and you use that oxygen for combustion, and then there's really no need for aggressive separations on the end. You need to get rid of water and some contaminants. But basically, you do the separations on the upstream end. So those are that's the toolkit, and again, with more options coming along the way. So the question, that I would have from a very practical point of view is, what kind of biomass sources are most amenable to capture? What will be the properties that would make it so you would decide to do this project in one location versus another? And then from a GCEP perspective is, if we were designing to purpose design or genetically engineer plants that could provide energy feedstocks for use with BECCS, what would be the attributes of that? And I hope today that you can give us some feedback on that this afternoon. The other thing is, which capture technology scales most cost effectively? If we're downscaling from 1 to 10 million tons per year to something less than 1 million tons a year, where will I be disadvantaged least by the economies of scale? And then the other thing is, if we've got a very variable biomass feedstock, is one capture technology preferred over another? I can easily imagine that oxycombustion might present some real advantages because the downstream processing to capture the CO2 is very little under those circumstances, so it might make it more robust against that situation. And then finally, we have to imagine where BECCS is going to be employed and what technologies will be able to be operated most reliably under those circumstances where it's actually deployed. There will be an entirely different workforce in North America and Europe than, for example, in Africa or developing Asia. So those are just very practical issues that I think we need to think about, but ultimately will inform our technology investment decisions. Okay, so that's it on capture. Compression is relatively straightforward. So let's move on to pipeline transport. Okay, so in the United States, we actually have thousands of miles of CO2 pipelines. They're shown on this map by those the lines you can see, primarily in the southwest of the United States, and also Wyoming, Montana, and more recently in the region around Louisiana and Mississippi. So we know how to transport carbon dioxide in pipelines. It can be done safely. We're transporting about 50 million tons per year today. So again, it's well understood. So we also understand a lot about the cost of building pipelines. And what this chart shows is something that's probably no surprise, but that basically the bigger the diameter of the pipeline, so the bigger the scale of the project, the more it's going to cost per kilometer of pipeline that you want to build. So if you just took a look at this and you saw diameter versus cost, you'd say, well, perhaps that there's not a big scale issue, but this is somewhat deceptive in that the amount of a fluid you can transport through a pipeline depends on the radius squared, not on or the diameter squared, not on the diameter itself. So the consequence is there is a really big penalty to try to transport carbon dioxide in smaller pipelines. So if we look at the diameter of the pipeline versus the cost, one can see that as you get to these smaller pipelines, which are those that you would want to build if you have very small projects, that it can quickly get very prohibitive to build these pipelines. So what this tells me is that we're very likely to end up with a situation where BECCS under these small-scale deployments will have transportation distances that are very short. So this issue of really co-locating the fuel source, the CO₂ sequestration site, and the demand for energy is going to be quite important. So this could change, however, if, for example, there was already a well-established infrastructure for transporting carbon dioxide associated with CCS and fossil fuels, where they're likely to build bigger facilities. And so to the extent that BECCS could follow on and build upon or take advantage of this infrastructure, that would be advantageous for BECCS. And it would make it so that longer distance transport would be quite feasible if they didn't have to bear the whole cost of building that long pipeline. Okay, so now moving on to the storage side. There are a number of storage options. You can put carbon dioxide into deep geological formations. There's a list shown there. It's also possible to put carbon dioxide into the oceans, either to inject it deep under the subsurface or the surface of the sea. The costs of that are high, and I don't believe that that's likely to be coupled with CCS. I think that if there is to be some consideration of using oceans, I think that the technology of bicarbonate formation, actually Greg Rao's here, and he's a developer of that technology, that may be a good scale match to these kind of BECCS projects. So there might be some opportunity for projects that are near the seashore. And then finally, there's the possibility of making solids. I haven't thought enough about that I mean, certainly that's difficult even at very large scale. And so it's not clear that it would work any better at smaller scale, but I think we're still in early times in that regard. So what I'll focus on is, again, the conventional approach, which would be to put carbon dioxide into deep geological formations. So then we get to the issue of co-location of the storage options with the need for electricity and source of biofuels. And you can take a look at this map. And the way to read this map is those areas that are dark are highly prospective in terms of having the opportunity to store CO₂. So they're sedimentary basins with oil and gas resources in them, so they're known to have the right kind of geology. The medium gray are those areas with sedimentary basins that are less well characterized or that don't have hydrocarbons in them, and so they are somewhat prospective. And those areas that are white are not prospective, at least with the current technology, meaning they're not sedimentary rocks. Now, into the future, basalt rocks may actually become feasible for CO₂ storage, but for the time being, that would be technology far out into the future. So I found it very interesting that North America has an enormous biomass resource, forestry resource. If we look at Europe, there's also good sequestration opportunities associated with North Sea, as well as some other areas. And I guess I must admit, when I thought about BECCS, I typically thought about areas where there was going to be a more rapidly growing demand for energy. But now my thinking has changed slightly, and places like North America and Europe, actually, it might be very, very interesting to think about that. So you can notice some areas with very rapidly growing demand for energy. For example, if you look at India, there don't appear to be great opportunities there. China, it's mixed. Okay, so within these regions, you can put carbon dioxide into oil and gas resources, deep saline aquifers, coal beds, and there are a number of studies, and I don't expect you to read this. This will be in the handouts. Basically, this is a recent compilation of information about the total capacity for storing carbon dioxide in all of these kind of formations, pretty much from around the world. And suffice it to say that in aggregate, it's quite large, and the sort of statements that are often used are that we have the capacity for hundreds of years worth of storage, sort of at any level that is practical to choose to do. Okay, so moving along. So what are we looking for in a storage site? We want it to be deep, greater than 1 kilometer, so that the carbon dioxide will be in a dense form. Second, we need to find a place with a good seal. So when we put carbon dioxide into the subsurface, it's buoyant, and it rises to the top of this structure. So if we think about things that drive costs for CCS, for storage, there are really 3 things. One is the characterization effort needed to make sure that you have a good seal and that you have porous rocks that can accommodate the CO2. So that's one of the things that can drive costs. The second thing that can drive costs are wells, that you need to drill deep wells and invest a significant amount of steel and cement in making sure that they're safely sealed all the way down to the point of injection. And then finally, there are monitoring costs associated with making sure that the carbon dioxide is staying in the formation that you've injected it into, and that it's not leaking at the surface, either near the wells or other places. So a significant effort is needed here. So in principle, could you do very small scale CO2 storage? There are no technical limitations. Actually, in some ways, the smaller the better. You put a small amount of CO2 in the subsurface, small pressure buildups, and so forth. However, there are cost drivers that the cost per ton of CO2 will be greater for smaller scale projects because to characterize a site, it's not so dependent upon how much carbon dioxide you're going to put in. For an injection well, one well may be able to take 1 million tons of CO2, but if you only have, 1/3 of that amount to put underground, well, you still need one well. So there are issues of scale there. And similarly, monitoring is not going to, the cost for monitoring won't be proportional to the amount of CO2 you're putting underground. And then finally, there are institutional issues associated with enforcing and ensuring that the injection projects are done in a way to assure the CO2 stays underground. So regulatory capacity, and depending upon where you're doing this in this world, that may or may not exist. So just a summary, certainly BECCS is influenced by scale. So this idea of, these very small scale deployments are going to be challenged. And I think that just assuming that the same technologies we're using for fossil fuel CCS may be not the right ones to implement given the kind of complexities of scale, variability of feedstocks, and so forth. So I think we need to take a look at that. And finally, and certainly BECCS will be a lot better off if we have a robust infrastructure for traditional CCS with fossil fuels. I find it difficult to believe that BECCS could, sort of get up and running on its own if there weren't already a well-established CCS plus fossil fuel infrastructure. And so I think I'll just wrap up with that.
Thank you, Sally. And we do have a few minutes for questions.
Yeah.
I just was wondering what kind of data exists to demonstrate the retention of CO2 in these kind of reservoirs. I mean, there must be some leakage, and I'm just not familiar with these data.
Right. Yeah. So There are a number of lines of evidence that are used to address that question. So the first is that we know that natural gas is retained in subsurface for tens, hundreds of millions of years. Similarly, we know oil is retained in underground for those same kind of time periods. Not only that, oil reservoirs and gas reservoirs often have a lot of carbon dioxide, and that doesn't seem to compromise the ability to retain CO2 for millions of years. So that's one line of evidence. Another is that we actually have now 5 CCS projects that have been operating. One for, nearly 16 years, the Sleipner project, and that's offshore of Norway, and it's a subsea injection into a saline aquifer. There's been innumerable amounts of monitoring that have been broadly made available to the scientific community. So there's that one. There's a project in Weyburn. There's another project in northern Norway. So all of the existing projects are heavily monitored, and there are research groups academic research groups from around the world who participated in those. And then the third sort of line of evidence, something which we have tremendous amount of experience, comes from CO2 enhanced oil recovery, which has been practiced since the 1970s, where carbon dioxide is injected underground to sweep the oil out of the pore spaces. And clearly those haven't been monitored to the degree that the other ones have, but those places where a close look has been taken, they haven't found evidence for leakage. So I'm not saying it's, well, okay, so it's important to, so the mechanism that traps the carbon dioxide under there, the seals actually act like a membrane. And so the carbon dioxide actually cannot penetrate into the seal except through the process of diffusion in the water phase. So a certain amount of carbon dioxide can dissolve in the water, and then you can have diffusion. But that's incredibly slow. So yeah, so I mean, of course, nothing's ever zero, but there are physical, there's actually a physical barrier, a membrane that traps the gas and the oil and so forth underground.
Yeah, the question is, José Moreira from the University of São Paulo, Brazil. When you were comparing a large-scale project with a small scale, it can be in favor of the small scale if we have a uniform technology, if we can believe that one size fits all. This is the only way to compete. And under this circumstance, looks to me that obviously the capture and transportation, this is one size fits all.
Right.
The problem is storage. So the solution is to have a huge pipeline infrastructure is the only hope that you can compete. And provide you have 100 or 400, let's say in the case of my country, there are probably 300 sugar mills in an area of 100,000 square kilometers. If you could make a pipeline infrastructure covering all this area by a reasonable cost, then probably you can compete.
Yeah, that would be really interesting to do that analysis. Yeah, and then you pick the perfect sequestration site. It makes a lot of sense. Yeah.
So, Sally, I'll pass on to you a question I get sometimes from CO2 skeptics, reservoir experts. That so they point out to me that the CO2 that is sequestered in saline aquifers will never be available for the carbon cycle again. You can't get it back out once it's permanently sequestered in there, or after it goes into dissolution. So their question based, I don't know if you ever get this question here, maybe you're insulated from these people more than I am, but they say, what if you're wrong and you're taking all this carbon out of the carbon cycle and you're putting it somewhere where you'll never get it back in the carbon cycle again? Is it? And so they're especially concerned where it's biomass, where it's actively in the carbon cycle, less concerned about fossil where it's kind of going back where it came from. But
right. I guess that would be a really good problem to have, but that's kind of a flip answer. So it takes a long time to dissolve all of the carbon dioxide. Sort of for a typical site, it's thousands of plus years. And actually, people are trying to design injection schemes to accelerate the dissolution because then you really have to worry about it less. But so we do lots of simulations of typical sites, and most of it is not dissolved in 1,000 years. And actually, Kareem Farhat, who's sitting actually right in front of you, he did his master's thesis on interim storage of carbon dioxide and looked at how efficiently you could pull it back out as long as it was not dissolved. And you can't get it all back out because you start producing a lot of water, but you can get some of it out. Yeah.
Okay, great. Thank you,
Okay.
Sally.
Yep.